Welcome to the group exhibit Hydrogen, Fuel Cells and Batteries at the Hanover Fair 2017. We are here at the Technical Forum and my name is Muriel Burkas. I would like to also our guests watching the presentation online through our live streaming today. Please join us of one of the last presentation of the Hanover Fair 2017 in the Technical Forum. Have some free coffee or some drinks. And I would like to start with the next presentation. It will be regarding highly accurate and lightweight pressure regulator in development for UAV drones and automotive. Please welcome on stage with me, Managing Director of Pressure Tech, Steve Yorke-Robinson.
Thank you. Okay, this is our first time at the exhibition, so I just want to spend a couple of minutes introducing the company, what we do, our background, and then discussing one of the technical challenges with pressure regulators, especially relating to hydrogen fuel cell applications. So we have 17 years experience of designing, manufacturing pressure regulators. Predominantly from 316 stainless steel, covering ranges from millibar up to 1,400 bar pressure, from line sizes from an 1/8 of an inch up to 2 inch. Our system is ISO 9000 certified. We do all our design, as I say, and testing. Every product we supply is 100% tested before shipment. And in 2014, we made a £750,000 investment in CNC machinery to cope with our growth, to offer quicker deliveries, more flexibility, and improved control over our quality of production. Our experience is probably a dirty word around here, but it's the oil and gas industry. And as the picture indicates, the sun is going down on the oil and gas business. So we are looking for new areas, and we're seeing an increase in interest in activity in hydrogen fuel cell applications. But the principles of our products, our pressure regulators, apply to both markets. The applications we've been involved with are everything from drone applications to autobus, and things like the automotive and stacker truck applications. And irrespective of the application, the product itself needs to be safe, accurate, stable, compact, lightweight, and economical. So all our product design covers those criteria. The function of a pressure regulator is to reduce pressure and attempt to keep the pressure as stable as possible, as the inlet pressure and the flow may vary. So typically you'll see a gas cylinder regulator coming from the gas bottle, and what you'll notice is as the gas is being consumed, the outlet pressure on a standard regulator will rise. So I want to go on to explain why that happens and what we've developed to overcome this situation. So the way a regulator operates, it's a simple mechanical equation. It's force equals pressure times area. And on the valve pin here, you'll see this is what we call as an unbalanced main valve. So the inlet pressure is acting against the seating area, pushing the valve pin into place. As you compress the spring on the regulator to set the pressure, that creates a loading force, and the first force that it has to overcome is this force here, which is your inlet pressure acting against the seating area. As soon as the spring overcomes this load, the valve will open and allow the gas, the high pressure gas, to pass through to the downstream side of the regulator, which then creates a second force, which is the area of your sensing mechanism times your outlet pressure. Because we've got a constant load from your spring once you've set your set point pressure, you've also got a constant value from the area of your sensing element and a constant value from the area of the seat. What happens is your supply pressure drops as your gas is being consumed. To keep this equation balanced, what you will see is an increase in the outlet pressure. So that's the curve that I showed at the start. So for every 100 bar drop in your supply pressure, typically that outlet pressure can vary from 1 bar to 20 bar increase. So it can be a significant variation in your set pressure. And the actual factor that determines that ratio is the area between your seat and the area of the sensing mechanism. One potential solution to this problem is what we call a two-stage regulator. So it's basically two regulators in series, passes through the first stage, and then is reduced down to a second stage. So that ratio you have, 100:1 on the first stage and 100:1 on the second stage, equates to about a 2,000:1 ratio. So it's a common design, it's readily available, but on the downside it is a large footprint, it's a heavier regulator. It's typically for low flow applications, and you do require interstage relief to protect the regulator from overpressurization. So what we propose and offer on the regulators is what we call a balanced May valve design. So now what you see is the inlet pressure working against the area of the seat, but it also works against an equal area in the opposite direction against the O-ring seals. So the same equation applies. Your loading force from your spring overcomes the load from your inlet pressure, but this force now is minimalized because you have the area of the seat minus the area of the O-ring. Again, you have a constant value from the spring, a constant value on the area of the outlet pressure, but the area on the supplies now becomes very negligible. And what that means that with every drop in supply pressure, the actual outlet pressure remains fairly steady and constant. So we have a video just showing this in practice between the balanced design and the unbalanced design. So first of all, it will show the regulator with the unbalanced design. Now on this test, we're only testing to 200 bar just to prove the principle or the theory behind the principle. So 200 bar on your input pressure from your gas cylinder. Obviously on a hydrogen fuel cell application that would be much higher, sort of 300 or 700 bar supply pressure. And you would set down to 1 bar on the outlet pressure, shown here. So now what we're simulating is the hydrogen or the gas being consumed, and you'll see here the outlet pressure is rising up to 2.45 bar. So without anything happening, just reducing your supply pressure, the outlet pressure is increasing. Now we'll put the balance regulator on test. And repeat this test with the same supply pressure, around 200 bar on the inlet pressure. And then decaying the supply pressure. Sorry, we'll set the pressure to 1 bar initially. So we've got a 1.08 set point. And this is showing it inside the regulator now. This is showing how the regulator is actually operating. So you compress the spring. You'll see your high pressure coming in through here. The valve opens to allow the gas to pass through to the outlet chamber, and that gas passes on both sides of the valve pin to keep that in a balanced position. Now, as the supply pressure is reducing, you'll see this outlet pressure remains fairly static. In fact, it goes up by about 0.1 bar, very stable control. And if you compare this then to the size of a two-stage regulator, you can see it's a lot more compact and economical alternative. So this particular application, the regulator has been developed. It is here if you want to feel the weight of this thing afterwards, but it's a lightweight regulator for a drone application. It's a safe design because it's piston sensed. Typically on these low pressure applications, you will use a diaphragm to improve your sensitivity. The problem with diaphragms is you can get hydrogen embrittlement, which can lead to fracturing or breakage of the diaphragm. So the piston sense is a more solid design. Maximum 300 bar supply pressure on this application, and we're reducing that 300 bar down to 0.5 bar in a single step reduction within plus or minus 0.1 bar accuracy. And the overall weight is 300 grams. And the decaying inlet pressure is now 1,000 to 1 with this design. So what we need to know from our customers, or hopefully potential customers, if you have applications of these criteria, the inlet pressure, the outlet pressure, flow rates, accuracy, etc., ambient temperature conditions, which will affect the O-ring selection, the connection type and size. The more of these questions we can get answered, the quicker we can offer the correct solution for your application. We have various regulators in our range. The main difference is what this CV value, the actual flow capacity through the regulator. So at the lower end here, this drone application, 0.06 is the low flow application. The MF series is going up to much higher flow rates, CV1 half-inch ports. And these are kind of the end applications they would typically be used or installed in. Okay.
Thank you very much, Steve.
Did I save you some time there?
Yes, that's good. Are there any questions from the audience? So you mentioned it's your first time here?
It is, yeah. And can I just say what a great show, and the support and the services from your team has been excellent. We've been to a lot of exhibitions, again, predominantly the oil and gas sector, but the services, the entertainment, the support has been outstanding. So we hope to see you again next year. Yeah.
Thank you very much for this compliment. I was wondering, I mean, you made the change from oil gas to this direction, or not completely?
It's not a complete change.
Not complete change.
We're edging both bets. And
okay. So you've already mentioned the difference on the fares, but what are the other differences you can see?
I guess the difficulty with the hydrogen fuel cell is still understanding from our perspective the standards that are required, what approvals need to be in place. People keep throwing at us the EC79 requirement for the automotive industry. And it's kind of a chicken and egg situation. Without the approvals, it's difficult to penetrate into the market. But without the market being there or the opportunities, it will be a significant investment for us to go through that process if we're not selling the quantity of regulators. The oil and gas is well established with its standards and requirements, so we kind of tick all those boxes.
I think we could also tell at this year's technical forum we had several presentations regarding the standardization and regulations. So I think it's an important topic we have to talk about and see how it will develop in the future.
Correct.
Thank you very much for your presentation,
Pleasure.
Steve.
Thank you.
So we are almost at the end of this year's technical forum at the Hanover Fair 2017. We have 2 more presentations left. The next presentation will start in about 1 or 2 minutes regarding on-site hydrogen generation with AEM electrolyzer by Inabata Europe GmbH. Please stay with us for the last 2 presentations today, and see you in a minute. Thank you very much.